Okay, in this video, we're continuing with the statistics textbook, Statistics by Friedman, Pisani, and Purvis. We're in part 1, the design of experiments. We've gone through chapter 1. We learned about controlled experiments. Now, in this video, we're going to go through chapter 2, observational studies. Okay, controlled experiments, that's what we learned about in chapter 1, are different from observational studies. In a controlled experiment, the investigators decide who will be in the treatment group and who will be in the control group. By contrast, in an observational study, it is the subjects who assign themselves to the different groups. The investigators just watch what happens. So that's the key difference between an official experiment, so like a controlled experiment, and an observational study. Fundamentally, in an observational study, the investigators aren't deciding who is in the treatment group and who is in the control group. The subjects are deciding. And as we look at examples of observational studies, I'll point that out to you. The jargon is a little confusing because the word control has two senses. A control is a subject who did not get the treatment, right? A controlled experiment is a study where the investigators decide who will be in the treatment group and who will not. And if you remember, part of what makes a perfect controlled experiment is that it's randomized controlled. Randomized controlled meaning that impartial chance procedure is used to assign subjects to the treatment or control group, kind of like flip of a coin. You flip a coin to see who goes into the treatment group, who goes into the control group. You're picking from a carefully chosen population, random population. And so based on that statement, what you can notice is that observational studies in most cases aren't as reliable as experiments, as controlled experiments. Really, in all cases, if you had an ideal controlled experiment, then that will always be more valuable, more reliable than an observational study. An observational study is just, you look at data that was just collected naturally, traffic data or any kind of data. It's not an experiment. You're just analyzing the data, right? So studies on the effects of smoking, for instance, aren't necessarily observational. Nobody's going to smoke for 10 years just to please a statistician. However, the treatment control idea is still used. The investigators compare smokers, the treatment or the exposed group, with non-smokers, the control group, to determine the effects of smoking. Yeah, so you're just saying you've got data on smokers and non-smokers. Who's a smoker, who's a non-smoker? Like the physicians are collecting data, like they ask you to write on your chart, are you a smoker or a non-smoker, right? Whenever you go to the doctor. So if you put you're a smoker, then they can look at the data and see, well, okay, how many of these smokers had some sort of a cancer and died, right? That's not an experiment. That's an observational study. That's what they're saying here. No smoker is going to smoke. Nobody's going to smoke for 10 years just to please a statistician. They're not choosing, okay, we've got this random population. We're going to have random people smoke for 10 years and then random people not, it's not an experiment. That's the difference. Any observational study, if you break it down fundamentally, that's what you'll see, that who's in the treatment group and who's in the control group, the subjects decide that, not the experimentalists. The smokers come off badly in this comparison. Heart attacks, lung cancer, and many other diseases are common among smokers than non-smokers. So there's a strong association between smoking and disease. If cigarettes cause disease, that explains the association. Death rates are higher for smokers because cigarettes kill. Thus, association is circumstantial evidence for causation. However, the proof is incomplete. There may be some hidden confounding factor which makes people smoke and also makes them get sick. If so, there is no point in quitting. That will not change the hidden factor. Association is not the same as causation. So you see the difference between association and causation. They've done this observational study. They see that a large percentage of these people who smoke are getting these diseases, heart disease, lung cancer. So there is definitely an association. There's no arguing that there's an association. But is it causation? So the confounding factor could be, on why it may not be causation, is maybe people who smoke have bad habits, health habits, right? If you did a true controlled experiment, you would have a mixture of healthy people who exercise and run, but a good mix but they would smoke, some wouldn't smoke, and you would see what happens. So for an observational study, like they mentioned, you still have a control group and a treatment group, right? The control group, non-smokers, the treatment group, smokers. But you really want to analyze how were these groups created? How were they, in effect, chosen? Right? I don't know if chosen is the best word, because they weren't chosen by the experimentalists, but the subjects chose themselves in a way. So how, in that sense, were they chosen? And if there is confounding, then you have to correct for that confounding. And this is an observational study. Statisticians talk about controlling for confounding factors in an observational study. Controlling for confounding factors in an observational study. One technique is to make comparisons separately for smaller and more homogeneous groups. So the example they give here is maybe the control group and the treatment group is made up of a lot more women than men. And furthermore, maybe there's a lot more younger smokers than older smokers. Well, women tend to live longer. They're healthier than men. And similar kind of idea with age. You can see how these are potentially confounding factors. So they're saying that you can separate the control group and the treatment group into smaller, more homogeneous groups. So you're just analyzing male smokers versus male non-smokers. You're analyzing different age groups only. You're separating the data into age groups. That's what they talk about here. Again, but you see how in an observational study, the experimentalist doesn't have as much control over the study as they do in a controlled experiment. Okay, the clofebrate trial. The Coronary Drug Project was a randomized, controlled, double-blind experiment. Okay, so this was a randomized, controlled, double-blind experiment, like we talked about in the previous chapter, whose objective was to evaluate 5 drugs for the prevention of heart attacks. The subjects were middle-aged men with heart trouble. Of the 8,341 subjects, 5,552 were assigned at random to the drug groups, and 2,789 to the control group. The drugs in the placebo were administered in identical capsules. The patients were followed for 5 years. Okay? One of the drugs on the test was clofebrate. So this project, they evaluated the effect of 5 drugs for the prevention of heart attacks. We're just focusing on clofebrate now, which reduces the levels of cholesterol in the blood to hopefully help prevent heart attacks. Unfortunately, this treatment did not save any lives. About 20% of the clofebrate group died over the period of follow-up compared to 21% of the control group. Okay, the control group was the placebo. A possible reason for this failure was suggested. Many subjects in the clofebrate group did not take their medicine. So the data, the initial data from this test for clofebrate, it showed that 20% of the group, this was randomized controlled treatment group, the clofebrate group, died over the period of follow-up compared to 21% from the control group, right? So you would, if clofebrate was effective, you would hope to see that the treatment group was, the percentage that died was a good amount less than the control group, but it was the same. But a reason for the failure was suggested that many subjects in the clofebrate group didn't take their medication, okay? That's a theory. So this is what they did. They said subjects who took more than 80% of their prescribed medication, because this was over a 5-year period, right? They tracked these people for 5 years. So the subjects who took more than 80% of their prescribed medication or the placebo were called adherers to the protocol, and then the others were called non-adherers. So we've changed the study. Now it's turned into an observational study. Do you see how? At first it was randomized controlled, but once it was found that some of the subjects didn't take their medication, and they're separating it into the adherers versus the non-adherers, now it's an observational study, because the groups now, the treatment groups, the control groups, the subjects decided, right? You see how that definition for observational study, the subjects decided which group they're in. For the clofebrate group, the 5-year mortality rate among the adherers was only 15%, compared to 25% among the non-adherers. Okay, so that's promising, right? For the clofebrate group, the adherers, 15% death rate, 25% non-adherers. That's promising. So maybe the clofebrate did work. This looks like strong evidence for the effectiveness of the drug. However, caution is in order. And you come here, So it says many adherers were different from non-adherers in other ways besides the amount of drug they took. To find out, the investigators compared the adherers and the non-adherers in the control group. In the control group 2, the adherers did better. Only 15% of them died during the 5-year period compared to 28% of the non-adherers. Okay, so yeah, if we come here, what they're saying is they also looked at the control group and you had that same difference from the adherers to the non-adherers. So it was more, the conclusion there is the adherers were just more responsible, healthier, took care of themselves better. This clearly shows that the clofebrate didn't help, right? You have 25 to 15 and 28 to 15. So the conclusion is that the clofebrate does not have an effect. Adherers are different from non-adherers. Okay, so you see how in an observational study, confounding variables are naturally introduced because the subjects are deciding which group they're in. There's going to be bias in that. Okay, they give some more examples here. Example 1, pellagra was first observed in Europe in the 18th century by a Spanish physician, Gaspar Casal, who found that it was an important cause of ill health, disability, and premature death among the very poor inhabitants of the Asturias. In the ensuing years, numerous authors described the same condition in northern Italian peasants, particularly those from the plain of Lombardy. By the beginning of the 19th century, pellagra had spread across Europe like a belt, causing the progressive physical and mental deterioration of thousands of people in southwestern France, in Austria, in Romania, and in the domains of the Turkish Empire. Outside Europe, pellagra was recognized in Egypt and South Africa, and by the first decade of the 20th century, it was rampant in the United States, especially in the South. Pellagra seemed to hit some villages much more than others. Even within affected villages, many households were spared, but some had pellagra cases year after year. Sanitary conditions in diseased households were primitive. Flies were everywhere. One blood-sucking fly had the same geographical range as pellagra, at least in Europe, and the fly was most active in the spring, just when most pellagra cases developed. So many epidemiologists concluded the disease was infectious and, like malaria, yellow fever, or typhus, was transmitted from one person to another by insects. Was this conclusion justified? Okay, so once they saw that this fly had the same range as the disease or the virus, it was concluded that it must be transmitted by insects. Again, this is an observational study. They're just looking at the data, the raw data. There's no experiment here. You see? Do you see the difference between observational study and controlled experiment? Okay, so is the conclusion that the virus is transmitted by insects justified? Well, another study found that it was actually caused by bad diet. It wasn't infectious, being transmitted. A lot of people in poverty ate only certain foods, like only certain corns that didn't contain nutrients that help to fight off this disease or virus or whatever it is. It says the flies were a marker of poverty, not a cause of pellagra. Association is not the same as causation. The flies were associated with pellagra, but it wasn't the cause. The diet was the cause. Okay, example 2, cervical cancer and circumcision. For many years, cervical cancer was one of the most common cancers among women. Many epidemiologists worked on identifying the causes of this disease. They found that in several different countries, cervical cancer was quite rare among Jews. They also found the disease to be very unusual among Muslims. In the 1950s, several investigators wrote papers concluding that circumcision of the males was the protective factor. Was this conclusion justified? So there definitely is an association between circumcision and the disease. The disease is rare among Jews and Muslims, both of which are circumcised. So there is an association. And again, this is an observational study. They're looking at the data. Where is cervical cancer common? What demographics? What genders? But this is all observational. There's no who's in the different groups, who's in the treatment group, right? Who doesn't have cervical cancer and who has cervical cancer is not being decided by the experimentalists. That's the fundamental definition of this. Okay, now what they found was that the cervical cancer was a sexually transmitted disease, and it had to do with the lifestyle of Muslims and Jews not as sexually active as other groups. So cancer takes a long time to develop. Sexual behavior in the 1930s or 1940s was the issue, right? This outbreak was in the 1950s. And so it was that sexually active lifestyle that was not as common or prevalent amongst Jews and Muslims that was the cause. All right, example 3, ultrasound and low birth weight. Human babies can now be examined in the womb using ultrasound. Several experiments on lab animals have shown that ultrasound examinations can cause low birth weight. If this is true for humans, there are grounds for concern. Investigators ran an observational study to find out at the Johns Hopkins Hospital in Baltimore. So an observational study, they're just looking at the data and seeing if they can find patterns in the data. And when they find a pattern, they look for confounding variables associated with those patterns. That's what you have to do in an observational study. Of course, babies exposed to ultrasound differed from unexposed babies in many other ways besides exposure. This was an observational study. The investigators found a number of confounding variables and adjusted for them. Even so, there was an association. Babies exposed to ultrasound in the womb had lower birth weight on average than babies who were not exposed. Is this evidence that ultrasound causes lower birth weight? So what they found was that they ended up doing a controlled experiment, and what they found was that the confounding variable was that babies who had ultrasounds, there was usually some sort of it was a problem pregnancy. That's why those ultrasounds were needed. And so these problem pregnancies were probably more of the causation for the low birth weight, not the ultrasound. And so they did a randomized controlled experiment to get more definite evidence. If anything, ultrasound was protective, right? You can rely on a randomized controlled experiment. If it's done well, nothing's perfect, but there's no substitute for a randomized controlled experiment. But you can see it costs money. It takes time. It takes resources. As opposed to just doing an observational study, you collect data, analyze the data, spend a few days analyzing the data, and you're done. Example 4, the Samaritans and suicide. Over the period of 1964 to 1970, the suicide rate in England fell by about 1/3. During this period, a volunteer welfare organization called the Samaritans was expanding rapidly. One investigator thought that the Samaritans were responsible for the decline in suicides. He did an observational study to prove it. This study was based on 15 pairs of towns. To control for confounding, the towns in a pair were matched on the variables regarded as important. One town in each pair had a branch of the Samaritans, the other did not. On the whole, the towns with the Samaritans had lower suicide rates, so the Samaritans prevented suicides, or did they? A second investigator replicated the study with a bigger sample and more careful matching. He found no effect. Furthermore, the suicide rate was stable in the 1970s, after the first investigator had published the paper, although the Samaritans continued to expand. So you would think as the Samaritans expanded more, the suicide rates would continue to drop. The decline in suicide rates in the 1960s is better explained by a shift from coal gas to natural gas for heating and cooking. Natural gas is less toxic. In fact, about 1/3 of suicides in the early 1960s were by gas. At the end of the decade, there was practically no such cases, explaining the decline in suicides. The switch to natural gas was complete, so the suicide rate by gas couldn't decline much further, right? They were saying that the suicides, people would commit suicide with coal gas, and since that wasn't as common, they didn't have an easy method to commit suicide. I guess they're saying like people don't want to shoot themselves. That's harder. It's more violent, harder to bring someone to do that. So they're suggesting that switching to natural gas, which is less toxic, people didn't have an easy way to commit suicide. Finally, the suicide rate by methods other than gas was nearly constant over the 1960s, despite the Samaritans. The Samaritans were a good organization, but they do not seem to have had much effect on the suicide rate. And observational studies, no matter how carefully done, are not experiments. But I mean, even to me, that's just a theory as well. The fact that the natural switching from coal gas to natural gas, there's definitely an association there, just like there's an association with the Samaritans. But that's just an observational study as well. I'm not saying that that the author of this book's conclusion is wrong. I'd have to read more in detail, but just pointing out no study is perfect. Okay, sex bias in graduate admissions. To review briefly, One source of trouble in observational studies is that subjects differ among themselves in crucial ways besides the treatment. Exactly. Sometimes these differences can be adjusted for by comparing smaller and more homogeneous subgroups. This was called controlling for, right? We talked about this. This is called controlling for the confounding factor. That's one method of controlling for. An observational study on sex bias in admissions was done by the graduate division at University of California, Berkeley. During the study period, there were 8,442 men who applied for admission to graduate school and 4,321 women. About 44% of the men and 35% of the women were admitted. Taking percents adjust for the difference in numbers of male and female applicants. Right. Yeah, that's what you use percentages for. Assuming that the men and women were on the whole equally well qualified, and there's no evidence to the contrary, the difference in admission rates looks like a strong piece of evidence to show that men and women are treated differently in the admissions procedure. The university seems to prefer men 44 to 35. Right. So for admission to graduate school, on the whole, all the graduate colleges, what percentage of women were accepted or admitted and what percentage of men were admitted? Total. 44% of the men, 35% of the women. So that seems like there's a bias towards men, right? Each major did its own admissions to graduate work, right? Each major. By looking at them separately, the university should have been able to identify the ones which discriminated against the women. At that point, a puzzle appeared. Major by major, there did not seem to be any bias against women. Some majors favored men, but others favored women. On the whole, if there was any bias, it ran against the men. What was going on? Okay, so if we look here, there's like over 100 majors at the school, but like a third of all the applicants was to the top 8 majors. And the pattern shown here is representative of the college as a whole. So we can take a look at what happened with these 8 majors. Okay, so here's the majors: men, women, number of applicants, and the percent admitted. If you look for each major, the percent admitted, men versus women, is about the same. So 63, 68, 37, 34, 33, 35, 28, 24, 6, 7. Except for the main major, where 62% of the men were admitted and 82% of the women. That's weird, right? We saw that overall. If you add up total number of males accepted divided by the total number of applicants, that's 44%. Add up the total number of women applicants accepted divided by the total number of women applicants, that's 35%. And the other majors, the other 90 majors, have nothing to do with this. This pattern is representative of the whole school. So that's weird, right? These are the B, C, D, E, and F are pretty much exactly the same. And then here you've got 62% males admitted and furthermore for the major with the most applicants. 62% men admitted and 82% women. But yet on the whole, it's 44% men to 35% women. That's weird. And so what happened here is, this is an example of Simpson's paradox. And this can be confusing. It took me a little while to grasp this, but it makes perfect sense. If we come back here, what's happening is some majors are harder to get accepted than other majors. What does that mean? So even if you have a major that's completely unbiased in regards to sex, completely unbiased, they're still going to only admit one of every, let's say, 5 women and one out of every 5 men, no matter what. So even if you're women, you're still going to be getting rejected from those majors. There's going to be a high rejection rate. There's other majors that it's the opposite. It's easier to get into. So the key is like this major A was easier to get into. You have 825 male applicants and 108 female applicants. So you have more males applying to the easier majors, the majors that are easier to get into, than the females. So females are getting rejected more on the whole, right? But it's about the major that they're applying to. So the conclusion was that it was more of a social issue. For some reason, women didn't want to apply to major A. They can't tell us the major. The university didn't allow it. But women, for some reason, aren't applying to the major A. Now, I mean, that could be an issue. Maybe there's some sort of a gender stereotype, but that has nothing to do with the university discriminating, right? Like if you look here, so E, 191, 393, 325, 593, right? But the acceptance rate is lower here, 37%, 34%. And I'm assuming it was the same pattern as you go down, right? Because there's like 90 more majors, so that adds up. So I'm assuming with these, when the percent admitted was lower, you were having more women applying to that. That's Simpson's paradox. It says that relationships between percentages in subgroups can be reversed when the subgroups are combined. Right? Let's come back here. If you just look at the subgroups, well, it's biased towards women, if anything. Right? It's all about equal, and then all of a sudden 82 to 62. You combine everything, now all of a sudden it's biased towards men, like in favor of men. That's a key idea they're wanting to point out. They're trying to drive home in this chapter, the authors, is these confounding variables with observational studies. You shouldn't have to deal with Simpson's paradox in a well-done controlled experiment. And so here what they decide to do is they do a weighted average of the percents. So let's come back here. They want to average the percent admitted for men and the percent admitted for women. But they weight this with using the number of applicants as the weight. So we haven't talked about what a weighted average is yet. But the average of the percents weighted with the number of applicants. So in other words, if there's a higher number of applicants, then that percent gets more weight in the average. So doing it that way, the weighted average, the admission rate for men is 39%, while the admission rate for women is 43%. So if anything, it's favoring women. But to me, I would say that's pretty much equal. Okay, so hidden confounders are a major problem in observational studies. As discussed in section 1, epidemiologists found an association between exposure, smoking, and disease, lung cancer. Heavy smokers get lung cancer at higher rates than light smokers. Light smokers get the disease at higher rates than non-smokers. According to the epidemiologist, the association comes about because smoking causes lung cancer, right? However, some statisticians, including Sir R.A. Fisher, thought the association could be explained by confounding the association between smoking and disease. Sir R.A. Fisher was trying to say that that's just an association, not a causation. Maybe smoking is healthy. Maybe the black lungs that they show, maybe that's something else. That's coming from something completely different. Confounders have to be associated with the disease and the exposure. For example, suppose there's a gene which increases the risk of lung cancer. Now, if the gene also gets people to smoke, it meets both the test for a confounder. This gene would create an association between smoking and lung cancer, right? So you see what they're saying here. If there's this gene that increases the risk of lung cancer but also gets people to smoke, well, that's not causing the lung cancer, right? That's a different issue. It's about it. You have to treat the gene, the habits of people with this gene. The smoking doesn't matter, right? So if for something to be a true confounder, it needs to be associated with both. In this circumstance, the disease and the exposure. And so Fisher tried to argue the association between disease, lung cancer, and smoking on the basis of genetic confounding. Nowadays, there's evidence from twin studies to refute this hypothesis. Okay, so they're just trying to give us a clear understanding of what confounding is, what a confounding variable is. Confounding means a difference between the treatment and control groups other than the treatment. Like it's a variable, but which affects the responses being studied, right? So it's not just a difference like you could have for the polio case. You could have some of the children be girls, some be boys. But if that's not affecting the responses, then it's not a It is a difference, but it's not confounding. A confounder is a third variable associated with exposure and with disease. Okay, so if we think about the polio case with the confounding variable of the lower income students, family students versus higher income family students, how is that how is that confounding? If you had low income family students whose parents didn't consent be the control group, and the consenting mostly high income students, family students being the treatment group, well, it affects the responses being studied because lower income students are more immune to the disease compared to the higher income. It's a third variable associated with exposure and with disease. These lower income students are just as exposed, we're dealing with children, to the disease. They're taking from these high polio rate areas, and they're more immune to the disease. Okay, so that's observational studies.